Have you ever really stopped to think about how you think? I mean, it all happens in a flash, but the journey just one single thought takes is, well, it's kind of incredible. We throw around this idea of the brain being like a computer all the time, right? Well, today we're going to pull back the curtain on that. We're going to dive into the information processing theory, which pictures your mind as this powerful biological operating system. So let's see how it actually works.
Okay, so it all kicks off with some kind of stimulus from the outside world. Just imagine you're walking down the street, someone stops you and they ask you a question. In just a few seconds, your brain has to pull off this amazing series of operations.
And this is going to be our test subject. A simple question. We're going to follow this little piece of information on its lightning-fast trip through all the different stages of your mind's architecture.
Think about everything that has to happen before you can even begin to answer. Your mind has to grab the words, figure out the order, understand what it all means, and then it has to search its massive memory banks, find the right info, and then put together a response. It's a lot. So let's trace that whole pathway right from the moment the sound hits your ears. So the very first stop for any information is what we call sensory memory. You can think of it as your brain's input buffer. It holds a perfect, totally unprocessed copy of what you just saw or heard. But here's the catch. It is incredibly fleeting. It lasts for just a fraction of a second before it's either used or it's just gone forever.
Now this is where it gets really interesting. Check out the difference between our senses. The visual trace, that's called iconic memory, it fades in about half a second. But the auditory trace, or echoic memory, that sticks around for 3 seconds or even longer. And there's a good reason for that. It gives your brain that crucial extra time to process spoken language and recognize the patterns in the sounds you just heard.
Right, so that sound of train station is really just raw data until your brain starts doing something with it. And that active process of analyzing and finding patterns in all that sensory data, that's perception. This is the moment your brain starts to actually make sense of the world around you.
This first stage of perception is purely data-driven. It's called bottom-up processing because, well, your brain is building meaning from the ground up. It's taking the basic sound waves, piecing them into syllables, then into words, and creating a meaningful pattern based only on the physical stimulus it got. No guesswork yet.
So once your brain has perceived the phrase train station, where does it go? It gets handed off to the next super critical stage, working memory. And look, this isn't some temporary storage shelf. This is the active, conscious part of your mind. It's the workbench where all the real thinking actually happens.
In fact, right now, as you're listening to me talk, it's your working memory that's doing all the heavy lifting. It's processing my words, connecting them to things you already know, and building a solid understanding. It's kind of like your brain's CPU and its RAM all rolled into one.
Okay, so if this is where all the action is, how much can it really handle at one time? Is there a limit to our conscious brain power?
And the answer? It reveals one of our biggest cognitive bottlenecks. As you can see, famous research found that our working memory can typically only hold about 7, give or take 2, chunks of information at once. Now that could be numbers, words, or complex ideas. This right here is the real reason you have to say a phone number over and over again to remember it.
But here's the thing. To understand the question, where is the train station? Working memory can't do it alone. It needs context. It has to reach out and access the brain's enormous, durable storage system, long-term memory. This is like the vast library where all your knowledge about the world is kept. And long-term memory isn't just one giant filing cabinet. It's split into 2 major systems. You've got explicit memory, which is all the stuff you can consciously bring to mind, knowing what. And then you've got implicit memory, which is unconscious. It's all the skills you just do automatically, knowing how.
Let's break down that explicit knowing what memory a little more. It basically comes in 2 flavors. Semantic memory is for general facts, like knowing what a train is, or the capital of Poland. Episodic memory, on the other hand, is your own personal highlight reel. You know, the memory of your high school graduation, or the last time you were at that specific train station.
And then on the other side of the coin, you've got implicit memory, which you'll often hear called procedural memory. This is your muscle memory. It's how you can ride a bike or type on a keyboard without consciously thinking about every single tiny movement. These are skills that just become automatic with enough practice.
So, how in the world does the brain keep all of this organized? Well, deep inside your temporal lobe, there's a structure called the hippocampus, and it plays this absolutely crucial role. It doesn't actually store the memories itself. Instead, it acts like a biological index, or a librarian, linking together all the different parts of a memory that are stored all over the brain so they can be pulled up as one complete thought. Pretty cool, right?
So now, with this huge library of long-term memories to pull from, our perception is no longer just bottom-up, it becomes top-down. Your existing knowledge and your expectations actually start to shape what you perceive. It lets you fill in the blanks. So if someone says something that sounds like a lot of our relatives, your brain instantly corrects it to relatives because that's what makes sense based on everything you already know.
So this entire model gives us a really clear, structured way to think about how we think. But comparing the brain to a computer definitely has its limits. So how well does this theory actually hold up under pressure?
While on the one hand, the theory's biggest strength is its beautiful structure. It gives us a clear roadmap for thinking about thinking. But on the other hand, critics argue it's just too mechanical. The brain isn't a clean, logical circuit board. This model really struggles to explain the messy, but totally crucial, influence of our emotions, our social lives, and our personal histories on how we learn.
And because of these limitations, it's really important to remember that this whole computer analogy is just one way of looking at the mind. There are other really powerful theories out there that offer different perspectives on how we think and learn.
For example, theories like constructivism say that we actively build our knowledge. We don't just passively process it. And connectionism sees learning less like a straight line in a computer program and more like the strengthening of these huge interconnected webs of neurons. They're not mutually exclusive, but they show there are lots of ways to model the incredible complexity of the mind.
So what's the big takeaway here? Well, turning a simple question into a coherent answer is an incredibly complex dance. Information flows from a fleeting sensory trace through that very limited mental workbench, gets cross-referenced with a vast library of knowledge, and is shaped by both the raw data from the world and our own expectations.
And that leaves us with one final thought to chew on. Now that you know about one of your mind's key limitations, that magic number 7, how might that change the way you approach learning a new skill, or maybe studying for your next big exam? It's definitely something to think about. Thanks for tuning in.